Hello and welcome to Beautiful Earth. My name is Erin McKinley, talking to you live from NASA Goddard Space Flight Center in Maryland. And we have a very exciting program for you today. First, I'd like to introduce our schools joining us today. First, we have Pleasant Valley Elementary in New York State. We have Abrams STEM Magnet, also in New York. Liberty Elementary in Virginia, as well as Universum Science Museum in Mexico City, Mexico. Thank you everyone for joining us. We also have plenty of our viewers on the webcast. Our webcast viewers may enter in their questions to us by sending them via email at dlinfochannel@gmail.com. Once again, dlinfochannel@gmail.com. Please send in those questions. We have a very exciting program for you today. With the help of science and art, you are going to witness Earth's severe weather in a whole new way. First, joining us live in the studio, we'll be having Kenji Williams, composer and musician of the Bella Gaia program, adding the art element to our program today. And today, joining us to help us understand the science behind Earth's severe weather, we have Dr. Dahlia Kirschbaum. Thank you for joining us today.
Thank you for having me.
Well, we are going to be discussing primarily a program that you are very familiar with, the Global Precipitation Measurement Mission, and how it helps us see weather around our planet Earth. So tell us a little bit more.
That's right. So Earth is a really complex system, and understanding how water, which is Earth's most precious resource, moves from the atmosphere to the ground to the underground is really important in understanding global water cycle. Now, GPM looks at precipitation, and it helps us to understand what's happening with rainfall, everything from light rain to heavy rain and snow, all the way from the tropics to the poles. Now, GPM is an international constellation of satellites. So what you see right here, it shows all of these different satellites orbiting in different places. They're for the US and international agencies, and they all work to provide a global picture of rain and snow everywhere around the world every 3 hours. Now, precipitation gives us a primary way to understand how weather behaves and how climate changes over time. And so really the difference between weather and climate, which is important to note, is that weather is sort of like our mood, how we feel on a day-to-day basis, whereas climate is like our personality over time. You know, sort of like, do we bring an umbrella today or do we bring it this season? And so what GPM and other NASA satellites are helping to understand is our global water cycle, and precipitation is one of the ways, the key contributors to our reservoir in the sky.
Excellent. Well, today we are going to take a closer look at 3 kinds of severe weather and their impacts. First off, hurricanes, then floods and landslides, and finally we'll wrap up with snowstorms. So first, let's take a look at hurricanes, something actually near and dear to my heart because having lived in the Gulf Coast area for 6 years, I've had to either hunker down or evacuate for hurricanes before, but NASA looks at them in a whole new way.
That's right. So hurricanes, they're like a heat engine. You need warm water, you need some pre-existing storms and some breezes to bring everything together. Now, just so we know, hurricanes and typhoons and cyclones are all the same phenomena, just in different basins. So we actually just finished the Atlantic hurricane season yesterday, November 30th, and we had a pretty light, pretty mild Atlantic hurricane season and a pretty active Pacific season. Now, from the vantage point of space, you can see some of these major storms in ways that you can't see on the ground. So the Tropical Rainfall Measuring Mission, or TRMM, which came right before GPM, has been looking 3-dimensionally at hurricanes such as this. This is Hurricane Katrina, and it shows layer by layer through storms these huge towers, which we call hot towers, and those are convective systems, convection within hurricanes that show when we might have a storm intensifying and where it might go. And so TRMM was the first one to look at these storms in 3D. Now GPM is actually able to improve upon that, looking at everything from the tropics all the way to high latitudes. And so what we're able to see, this is a graphic of Hurricane Gonzalo, which affected the Atlantic. And what you're looking at here is heavy precipitation in the reds and pinks and lighter in greens. And then what GPM can see is also the blue, which is the snow and the ice on the top of the storm. And looking at all of those together really helps us to understand the dynamics of the storm, where it's going. But one of the things that we haven't been able to do as of yet before GPM was look at storms like Hurricane Sandy, for example. Now, Hurricane Sandy affected the East Coast. This actually shows wind speeds, and it shows the speeds. The red is really, really intense winds, and it shows it moving its way up the East Coast. Now, GPM was just launched in February of this year, and before that, which is when Hurricane Sandy occurred, we wouldn't have known what the rainfall was like in this storm as it was off the coast. Now, GPM can really allow us to have that global picture from the tropics all the way to the poles.
That's fantastic. So while TRIM is a wonderful program, wonderful mission, it's really limited because it's going around the equatorial region of our planet, while GPM is showing us the more global, as it says in the name, the more global view.
That's right.
Excellent. Well, thank you so much, Dahlia. Now we're going to take a look at the severe weather through the eyes of music and our wonderful guest, Kenji Williams. So please go ahead. That was beautiful. Thank you, Kenji. A whole new way of looking at hurricanes. Now let's go out to the schools. I'm sure you have plenty of questions for us. So we will be following a round robin format. I will call out your school's name, which will be your signal to unmute your microphone. Then we will go to each school asking for 2 questions. We'll go through hopefully 2 rounds of questions each. So let's go ahead and start with Pleasant Valley Elementary in New York State. Open up your microphone, please.
Have the images sent back from the satellite reveal any findings about Earth?
Unfortunately, I did hear a little bit of feedback. Could you please repeat your question?
Right here. Have the images sent back from the satellite reveal any surprises about Earth?
Interesting question. Have any of the images we've seen have actually issued any surprises?
Yeah, actually, so with the GPM satellite, what it's coming back as is it's information in the microwave frequencies. So we're seeing rainfall and snow like we haven't seen before. And so one of the things that we first noticed about is when GPM was first launched, one of the first images we saw was a storm in the northern Pacific. And it was the first time we were ever able to see ice and snow in an extratropical storm like this. And that type of data is actually telling us a lot about storm dynamics, especially at high latitudes. So people that are in Japan and elsewhere are really, it's very helpful to see how these storms develop.
So right off the bat, GPM was giving us some fantastic information.
That's right, the first image out of the bat.
Excellent. Well, that was a wonderful question. We'll go for one more to Pleasant Valley, and then we'll go to Abrams STEM Magnet. So Pleasant Valley, go ahead with your next question.
How does the satellite get repaired?
Good question.
You know, it's a challenge. So we spend years and even decades creating these satellites, going from the infant stages all the way through to launch. And so we very much hope the engineers at NASA and all the partner agencies do a great job of testing everything. But once the satellites get up there, right now, there isn't any way to repair them. Sometimes we can do computer fixes, and that actually helps a lot. We do those quite frequently just to make minor adjustments. But if a part breaks, there tends to be a redundant part, so spares often, but there isn't a way for this satellite to be repaired by astronauts right now.
Good question. Thank you so much, Pleasant Valley. We'll come back to you in the second round. Now let's go out to Abrams STEM Magnet, also in New York. Go ahead with your first question.
Hi. How many satellites are there in the GPM project?
Excellent question.
That's great. So GPM has about 8 to 10 satellites that are up there, and they come from partners in the U.S., the Department of Defense, NOAA. There also is in Japan, in Europe, even in India and France have a partnership. And so it's really a very international partnership that's really making this this mission possible. So about 8 to 10 satellites in just this, what we're calling a constellation.
Excellent question. One more from Jack Abrams. Go ahead.
How do you make 3D models of a hurricane?
You know, GPM provides very important data for weather forecasting agencies to make these 3D models of hurricanes. Now, there is a group within NASA that does do this, but that group at NASA, in addition to the National Hurricane Center, centers in Europe and all over the world, take this data to make their models. And what's important to note is that we don't want to rely on just one model to forecast where a hurricane is going. We actually need multiple models. It's called an ensemble to really get a sense of where we think this storm might be going, which is what happened with Hurricane Sandy.
Exactly right. Excellent questions. Thank you, Abrams. We'll come back to you in the second round. Let's go out to our friends in Virginia, Liberty Elementary. Go ahead with your first question.
All right. First class. Tejas.
Where do you get all when the satellites are outside, are they somehow connected, and do they have like a country they look at each time, like one satellite looks at one country?
Very good question.
So the satellites that are in GPM and many other satellites as well, so they're orbiting the Earth. So they're always taking these different pictures of places as they orbit. It's called the swath. Now, they actually talk to each other and they are able to relay their data down through what's called these teleconnection satellites. It's called the TDRS satellites. And so, they send their signals out these satellites and it comes down to the ground. And we're able to process that data back at NASA Goddard, right here where we're sitting. And so by having that network, it's able to look at these, each satellite has a different picture that together, sort of like a puzzle, when you put them all together, you get that global picture.
Excellent question. We are going to go for one more out to Liberty Elementary. Go ahead.
Zach. Greatest class.
What has been the biggest hurricane that one of your satellites has seen?
That's a great question.
Wow.
So, well, we've seen, so TRIM has been up since 1998, which might be before many of you were born. But it's been providing unprecedented data of tropical storms and hurricanes all over the world. TRIM has seen Hurricane Sandy when it was in the tropics, Hurricane Katrina, and even recently Typhoon Nuri and all of these really big storms that are affecting the Pacific, which sometimes we don't always hear about in the U.S. So we've been able to see hundreds and hundreds of storms, and actually the data that we have from the TRIM is able to help correct the tracks of these storms to know maybe where we're supposed to evacuate, such as in the Gulf Coast, when you get these extreme storms. And so all of this data coming not just from these satellites, but from weather, the satellites that come from NOAA and elsewhere, provides us all the clues we need to help make informed decisions about evacuations.
Really is teamwork at its finest. Excellent questions. Well, we will go to you once again. Let's go now down to our friends in Mexico City, Mexico, at the Universum Science Museum. Go ahead with your first question.
Thank you. Here's the first one.
Thank you. How is the wind speed measured by the satellite?
How is wind speed measured by a satellite? That's fascinating.
Well, wind speed is actually, TRIM doesn't and GPM don't measure wind speed, they actually measure precipitation. But there's other instruments called QuickScat, for example, that look at, for example, they look at ocean waves, and they can figure out, based on signals that are scattering from the actual waves, they can figure out how fast these storms are going. And so other satellites are able to tell information about wind speeds or even humidity and temperature. And so all of those factor into telling us more about hurricanes.
And speaking of teamwork, we also have ground sites as well with wind speed and humidity.
Absolutely.
So we can gather that information from the ground and also from satellite data.
Absolutely.
Wonderful question. One more from Mexico City. Go ahead.
Thank you. What instrument do you use to measure all that's shown in the video?
Wow.
So I'll give you the brief answer of that. But GPM has two instruments on board. One is it's a radar, and so it essentially sends a signal out and it scatters off particles, rain, snow, hail, the like, and it gives us a three-dimensional picture of rainfall, and that's a three-dimensional images you see as they were stacking upon each other in the visualizations. But there's also another instrument that's sort of like an X-ray. If the radar is like a CAT scan of the body, the other instrument is a radiometer. It's like an X-ray, and so it can really help to tell about light rain, heavy rain, and snow. And so together, where those two instruments intersect, it's really powerful to better understand everything from the individual particles, what we call the microphysics, all the way to the big, huge structure of the entire storm. And so these instruments are actually the most advanced instruments in space to measure precipitation.
Excellent. That's wonderful news. Well, these questions have all been fantastic, but unfortunately we need to keep on going and learning more about severe weather. We do have one webcast question from our friends at Sable Palm Elementary in Florida. Eric wants to ask, how did you come up with the idea of building GPM?
Well, GPM, so TRIM was conceived very long ago by a person named Joanne Simpson, who's passed away, and her legacy has remained all the way through for GPM. When TRMM was launched actually on Thanksgiving about 17 years ago, they started talking about GPM and what was the next great thing they could learn about precipitation. And so we've been in the decade and a half that it's taken to kind of move from the ideas stage all the way to the launch. It's taken that long to really build and understand what we're looking at for NASA.
That's incredible.
So it's been a long time in the making, and it's exciting.
Excellent questions. Thank you once again to our schools and our webcast viewers. Keep those questions coming. Webcast viewers, you can once again send those questions to dlinfochannel@gmail.com. Keep them coming. Our next topic is actually something that is very near and dear to Dahlia's heart as part of her major research, floods and landslides, which is a very interesting topic to study.
Thank you. Yes, so what my role is as a scientist at NASA is to work with satellite data from rainfall and topography, so looking at the slopes and the soil types, to really figure out where and when landslides are occurring. Now, landslides tend to occur where we have steep slopes, we have some loose soil that's been saturated. This is an example of a major landslide that was in El Salvador, but landslides all around Central America and South America and the U.S., nearly every state has landslides. And so it can be caused by heavy rainfall, earthquakes, and even freezing and thawing. Now, floods occur when when the soil has already been pretty saturated, and the ground really can't absorb any more water from overflowing rivers or runoff from mountains. And so it causes a buildup of water that we can actually see from space. And so by looking at, this is an example of some Thailand floods, we're able to see these images and different data from space to get a broader picture of Earth and try to anticipate where we might have floods and landslides in the future. Now, GPM is building off of TRMM's capabilities, so we're actually able to use higher resolution or more detailed measurements to get a much better understanding of where and when we might experience floods and landslides in near real time, which means right away.
Excellent.
And so this is just an example of some ideas of models that we're currently developing at NASA and other places to tell us what might happen with these extreme events and how they might be changing in a changing climate.
Excellent, and really this is not only fascinating information for the science, but it's also great for community safety as well.
Absolutely. So NASA and the researchers here and elsewhere try to take this data and provide it to decision makers to make informed decisions about evacuations and where to relocate people when there's a disaster.
Excellent. Well, thank you again for that amazing information about floods and landslides. Now let's take it in a whole new perspective with the help of our friend Kenji Williams. Thank you once again, Kenji. Let's go back out to our schools for another round of questions. You had a fantastic round first off. Let's keep it up. So let's first go out to Pleasant Valley Elementary in New York. Go ahead.
How will the GPM satellite help us better understand the water cycle?
The water cycle, and how does GPM help us?
Well, GPM is helping us understand our reservoir in the sky, but there's a lot of other parts to the water cycle. So when we need to know how much rain and snow is falling around the world to be able to understand where our fresh water is coming from.
Right.
But other Earth science satellites that we have here at NASA tell us about other parts of the water cycle. A mission that's launching called SMAP in late January of this year is telling us about soil moisture and active in freeze-thaw states of the soil. Groundwater, we're looking at satellites that can tell us where there's big groundwater, such as in California, where we're having a massive prolonged drought.
Yes.
And all the way through to looking at glaciers and estimating snowpack, and which we'll talk about in just a bit. So all of that together is really important. We need GPM in addition to all these other Earth science satellites that tell us what's happening with the water cycle.
Yes, excellent question. We'll take one more from Pleasant Valley. Go ahead.
Are there plans to launch another GPM satellite?
You know, as I mentioned before, you know, we talked about GPM as TRMM was still, you know, providing data in its first years, and there's already talk of what new ideas we can pursue. So we won't build another satellite because we want to expand the bounds of what we understand about precipitation. Yes. So we're always talking about what's the next thing we need to or want to understand about our Earth and about precipitation. And so yes, there's already movement to find a new and exciting next satellite that follows on after GPM.
Excellent questions. Thank you once again, Pleasant Valley. Let's go stay in New York State and go to Abrams STEM Magnet. Go ahead with your first question.
Is GPM looking to observe weather on other planets?
The other planet question.
Well, understanding weather on other planets tells us a lot about weather on our planet and into the galaxies. But right now, GPM is really focused pointing downward at Earth. And there's a lot still to learn about our Earth, about our weather and our climate in a changing climate.
That's right. We do have a few missions orbiting around Mars, for example. MAVEN is taking a look at the atmosphere, while the Mars Reconnaissance Orbiter, or MRO, has been helping us take a look at a wide variety of things, including the atmosphere around Mars. So check out those missions. Today we are focused on planet Earth, our home planet. So GPM is helping us with that. Thank you very much. We'll take one more from Abrams.
Do the satellites have like a pattern they go around Earth, or do they just go everywhere that the satellites didn't go before?
That's a great question.
Excellent question.
Well, there's a lot of satellites and debris up in space, and so it really requires a lot of finesse to make sure that the satellites don't hit each other. And so GPM has these orbits that we're able to track, and we provide data from actually where we're sitting at NASA. It provides information to the satellites to tell it where to orbit and even how to maintain its altitude. So it goes into standard orbit just like all of the other satellites, but computers in the ground talk to computers on the satellite to make sure that they're in the right position, because it's very important.
Wonderful question. And we'll go for one more at Abrams. Go ahead.
Why, in the video about the clouds, did it seem to dissipate around the equator?
Very interesting question.
Very good. So what we're looking at is, in some of the animations, is actually hurricanes. Now, hurricanes can't form on the equator, and the reason for that is the Earth is spinning, so it makes one rotation every 24 hours. And because of that spinning, the storms can't actually start to rotate when they're exactly on the equator. So storms, if you look at all of the storm tracks, they tend to form about 5 degrees plus or minus above the equator or below the equator, and move poleward, and that is because of the rotation of the Earth. And the other thing is that the movement of circulation, atmospheric circulation, we actually have a lot of rainfall around the tropics. So it's called the Intertropical Convergence zone is the technical term. But the actual storms themselves, hurricanes, cannot form on the equator, and very rarely do they dip into the other hemisphere. They always go out from where they started.
Fascinating. Very good question. I'm learning something too today. Wonderful. Let's go to our friends in Virginia at Liberty Elementary. Go ahead with your next two questions.
Go ahead, Bert.
Why do you need to have very fancy and big cameras to take different pictures of the Earth in three-dimensional shapes?
Could you repeat that one more time? We heard a little bit of feedback in the beginning.
Why do you need a big fancy camera to take pictures of the hurricanes in three-dimensional shapes?
Why do we have GPM?
Why do we need big fancy cameras? That's a great question because they cost a lot of money.
Yes, they do.
But it's really important to have big fancy cameras. There's lots of different types of instruments in space, not just with GPM. We have these, they're literally cameras on board the International Space Station, on board other satellites that take pictures just like we can see, and down to very, very small scales. With GPM, because the importance of understanding that three-dimensional structure is actually to see how precipitation is not only distributed, but how it's moving in the atmospheric column. And so looking at everything, not just at one consistent picture like an X-ray, but actually a three-dimensional picture, tells us a lot about these huge convective towers that we were seeing in Hurricane Katrina earlier, as well as where we're having cold precipitation like ice and snow on the top, and where we're having more intense, warmer precipitation on the bottom. So we need to look at that three-dimensional picture to get there.
Very good. One more question from Liberty. Go ahead.
Elijah, how much would it cost and how much did it cost to start a program like GPM?
Cost is very important. So GPM, in all total, after about a decade, cost $933 million. Now, what's interesting is it's actually a partnership between NASA and Japan, the Japan Aerospace Exploration Agency. And so we were able to share some of those costs because Japan launched the satellite.
Right.
But if you think about it, GPM, in terms of an investment, was about 2 or 3 water bottles per person in the United States. And that's looking over 10 years or more. So
that's excellent.
Yeah, so that's the answer to the question.
Very good. Well, thank you, Liberty. We will go down to our friends in Mexico City at the Universum Science Museum for your next two questions. Go ahead.
Okay.
Thank you. With all this information about the Earth and all of that, we are able to prevent a city from a flood before it happens.
Very good question. So with this information, can we actually prevent these from happening?
Right. You know, right now, NASA is really in the business of providing data. So trying to provide data so that emergency responders or even people that are making the forecast can better understand where they're happening. Now, trying to prevent floods or landslides is really an engineering challenge. And so that's something that at the local level and the government level, that's the kind of investment you need. You need to have the data provided to understand where they might happen, and then the engineering know-how to figure out how you can build levees, for example, or barriers to prevent from these major hazards. But in many, many, many instances, you can't prevent it. You can just mitigate or help to move the people so that they don't go into harm's way.
That's right. Very good question. We'll take one more from Universum. Go ahead.
Yes, thank you. Which country is the one that has had the most flood?
That's a great question. You know, I don't know the answer to that. There are many hotspot areas for floods. And in fact, as I said, floods happen. There's nearly 1 flood a day in the world. But there are many hotspot areas for them, all in the US, in Europe, Central and South America. Now, I can say for landslides, actually, there are some hotspot areas for landslides to occur. And those are tend to be in India and Nepal and the Philippines. In Central America, really anywhere where there's active mountain ranges and a lot of rainfall, all the way down into South America. So we have some really hotspot areas that we know to focus on with data. But as you mentioned before about ground validation, which is the way that we check how the satellite is performing based on ground measurements, we need a lot of that data both to understand our precipitation, how much is falling, but also to understand hazards like floods and landslides.
Excellent questions. Thank you once again. We do have some wonderful questions coming in from the web. Let's go to Blackford Elementary, California. Allison wants to know, how do you launch satellites?
Very carefully.
That's right.
You know, it takes a lot of engineers. There were over 500 engineers that worked on building GPM, in addition to the people that worked on launching it. As I mentioned, that the GPM and the TRIM satellites were both launched from Tanegashima Space Center in southern Japan. And so we have other satellites that are launching from Vandenberg, California, even some that are starting to launch from Kennedy to look at how we can send people and supplies to the International Space Station. So it takes a lot of engineering prowess to make these happen.
Excellent question. We have one more. This time we're going from Texas. Cedar Valley Elementary, we have our friends want to know, with the new GPM capabilities, we know the GPM can determine when and where a storm might occur, but can it determine the impact of a storm?
So those are a separate type of models. You know, we have a lot of numerical weather prediction models and hurricane models that can tell us where a storm might go. But the impacts, you know, looking at storm surge, for example, or high winds, those are other models. Those are loss models and catastrophe models that other people have made.
Sure.
But yeah, there's a lot of different information that goes into it, and what GPM is providing is actually the science data to figure out about flooding, about rainfall, and about the intensity of storms, so that other modelers can figure out the impacts.
The impact. Excellent questions. Thank you once again. All of our schools, our webcast viewers can send those questions. Keep them coming to dlinfochannel@gmail.com. Please keep those questions coming. We're now going to go into our final topic today. December 1st today is the first day of meteorological winter. And our next topic is something that we are probably going to be worrying about, especially in this area, for the next few months to come. That's snowstorms.
That's right.
So very interesting topic.
Yeah, absolutely. And you know, some people have already experienced a tremendous snowfalls. Like Buffalo, New York had 5 to 6 feet at the beginning of November. So, you know, in the last 10 years, scientists have really shown that we are able to look at snowfall or falling snow and snowpack in ways that we haven't been able to do before. In fact, the project scientist, the lead of GPM, Dr. Gail Scrofonic-Jackson, said that we were measuring rain like this 40 years ago, but only just starting with snowfall. So, you know, snow is an important primary resource of fresh water in mountain regions. For example, the snowpack in the Sierra Nevadas accounts for 1/3 of the water supply for all of California. And snowmelt, as snowmelt enters the water cycle, it provides both drinking water and sources for irrigation. Now, with droughts and with climate change, that snowpack is actually starting to shrink, and so water resource managers are very concerned about trying to find exactly where and when we're going to have these freshwater surges or freshwater deficits.
Yes.
Now, snowflakes themselves come in a wide variety of different shapes and sizes. And with GPM, as I said before, you know, the ability to look three-dimensionally through the clouds allows us to look at individual snowflakes through time. So one way is to basically get all of the information scattered back from the particles from snowfall to really understand where we're having light rain, where we're having heavy rain. So what you're seeing here is all the different channels that GPM can sense types of snow at, from light rain to heavy rain and ice. And the reason that that's important is because knowing if something is, you know, if it's light rain or if it's snow or if it's ice within the particles tells us a lot about the atmospheric circulation and storms in general, and helps us to really modify our models to look at stronger or heavier rain events. And in a changing climate, that's really important.
Absolutely. Wonderful, wonderful topic. And now let's take a look at snow. I know we've all seen snow probably from the end of a snow shovel in this area, but now let's take it through the eyes of Kenji Williams. So let's take a look. Thank you. That was fantastic, Kenji. Now let's go back out to our schools for our questions, starting with Pleasant Valley Elementary for your next two. Go ahead.
How many times per day does the satellite orbit the Earth?
How many times does GPM on average orbit?
So GPM orbits about every 90 minutes, and it crosses the same point on the Earth about every 2.5 to 3 days, depending on where you are. But about every 90 minutes, it makes one orbit.
Excellent question. So on average, the speed's probably 17,500 miles per hour?
Sure.
Yeah. How do I know that? That's the average speed of the ISS.
There you go.
In order to maintain an orbit, you have to go at least 17,500 miles per hour. Excellent question. One more from Pleasant Valley. Go ahead.
How much fuel does the satellite have on it? Does it use solar energy?
Very good question.
Yes, it does. So it has a huge fuel tank on board, many kilograms of fuel that I am blanking on the number on, but I think it's 750 kilograms of fuel. And it also uses solar panels. Now, why do you need both? Well, solar panels help, the satellite operate day to day, but the fuel is actually needed to maintain the orbit. So just like the ISS orbit, the International Space Station orbits at a certain altitude, GPM needs to maintain its altitude, which is about 205 miles or 450 kilometers above the Earth, and that helps it to make sure that the instruments are operating properly and they see the right distance.
Very good question. Thank you very much. We'll go out to Abramstead Magnet for your next two questions. Go ahead.
What was the biggest snowstorm?
The largest snowstorm. Maybe we'll just go with this past year. Largest snowstorm.
This past year, yes. Yes. In time, I think it depends where you are, to be completely honest.
Yes.
We had some pretty epic snowstorms a couple years ago here in the Washington, D.C. and Baltimore area. This year, the Buffalo actually had a huge amount of snow, 5 to 6 feet, and already in the Midwest, which I'll mention in just a little bit actually, we've already had some snowfalls as early November.
Yes.
And so it looks to be, in terms of the projections for our area, to be a pretty snowy and cold winter ahead of us. But the biggest snowstorm, I think it depends on where you are.
That's right. Everyone has their own opinion, their own snowstorm story, I'm sure. We'll have one more from Abrams. Go ahead.
How did you find the name of the hurricanes?
How do you find the name of the hurricanes? Well, actually, there's a list. If you go to NOAA's website, the National Hurricane Center website, they have a list of the named storms, and they go through them alphabetically, and they actually retire names of really big storms like Hurricane Andrew or Hurricane Katrina.
That's right.
But there's a list of storms, and when they run out of names for that year, they go into numbers of storms. So there will never be a shortage of named storms. But you can actually see what the names are and what they'll be into the future on NOAA's website.
That's right. It comes out in middle of May, I believe, before June 1st.
Yes.
I think every year. Very good question. We will go now to our friends in Virginia, Liberty Elementary. Go ahead with your next two.
Ashley.
A little louder, honey.
How far away is the satellite dish from the Earth?
How far away are the satellites on average? So
on average. So there's a lot of different types of satellites. GPM is what's called a low Earth orbit, kind of like the International Space Station. So it's about the distance from Washington, D.C. to New York City, about from the Earth, if you go straight up, about 250 miles, or 50 miles, 405 kilometers, sorry.
Lots of numbers.
Yes. There's also higher satellites that are about 800 kilometers, and then there's some that are like the GOES weather satellites, where you see oftentimes on the news or the Weather Channel, and those are 10,000 miles away. So there's so it really depends on what type of satellite, but you need different types of orbits based on the instruments that you have on board the satellites.
Very good question. One more from Liberty. Go ahead.
When you were showing us the pictures, we saw like a house and some trees. Are those things really there, or does the satellite just make it up?
Satellites, so I don't know if you're referring to the floods or what have you. So there's a lot of different satellites that can take pictures in different ways. But they're able to either see what's on the ground, such as looking at, do we have water or do we have a house, or in landslides, is it bare earth or is it forested land? And then other satellites like GPM look at above the surface. It looks at precipitation, but it definitely isn't able to make anything up. There's a lot of different satellites that give different pictures of different parts of the world.
Yeah, excellent questions. Thank you once again, Liberty Elementary. Now we'll go to Universum Science Museum in Mexico City. Go ahead.
Here is the first one.
Thank you. Does the GPM can calculate if there will be acid rain in contaminated areas?
Acid rain.
Interesting.
So, GPM doesn't look at the chemistry of the rain. And so there's other satellites that can look at water molecules, or they can look at what's happening on the surface, even looking at ocean temperatures, or if there's, toxic algal blooms in some of our oceans. But GPM is really only looking at the precipitation itself. It can't tell the chemistry of the actual individual raindrops.
Great question. One more from Mexico City. Go ahead.
Why there is less possibility in a desert to rain if the clouds are able to move with the wind?
Ah, good
It's
question.
A very, very complex question.
Yes.
I'll take a stab at answering that quickly. So if you look in atmospheric circulation, we have high areas, there are high pressure areas and low pressure areas. So if you take the Sahara, which is a really, really big desert, or even parts of Mexico, there you actually have air that's rising at the equator and sinking in those latitudes. So in Mexico or in the Sahara, air is actually sinking, and it prohibits precipitation from forming. So it creates a high pressure area where rain doesn't want to form. But there's still clouds, they just tend not to be the clouds that produce major rainfall. And so winds are moving from, they're moving from the equator all the way upwards, but there's also winds that are moving across as the Earth turns. And as we talked about before, the Earth turning is a major force and causing the atmosphere to circulate and have weather circulating. So that's the main reason, is you have these big air pressures that are sinking at those desert regions, and so rain can't form there.
Excellent questions. Thank you to our friends in Mexico City. We do have a few more webcast questions. We have actually a question in local areas. Zeke in Maryland wants to know, will there be more clouds with global warming? And if so, what impact will they have? And that really brings up, what is the impact of global warming? Will there be more extreme weather with that?
Right. So understanding kind of how the Earth is warming, and we know that the ocean temperature is rising and the atmospheric temperature is rising, it will change the dynamics of cloud formation. Looking at how much water vapor we have and where that will form.
Right.
Warmer water will create more vapor, which will create more clouds in some regions and less clouds in others. Now with extreme weather, I sort of like to think of a metaphor of the NBA basketball. So if on average, there are 6 slam dunks a game with players in a basketball game, and then you raise the floor 6 inches, and now on average there's 10 slam dunks. You never know which slam dunk is really attributed to the raising of the floor, but you know that you've seen more. And that's sort of the same with extreme events.
Right.
We fully expect as scientists that we're going to have more extreme rainfall, more intense rainfall, more droughts, more heat waves, more cold. All of that is part of extreme weather, but it's related to climate change. It's just you can't attribute any one event to climate change itself.
Excellent question. We have one more from our friends in South Carolina, Doby's Mill Elementary. They want to know, after all of the spots on Earth are covered by GPM, are there any dead spots?
The very, very top of the North Pole, or even the polar regions, are very difficult to measure precipitation.
Really?
It also tends to be deserts in that area. That tends to have very little rainfall at the very top of the poles, and that's because everything's orbiting in different ways. And also parts of the tropics, because the Earth is shaped the way that it is, we tend to have a little bit less coverage in the tropics because it takes longer for them, there's less coverage over the areas, whereas the satellites are orbiting or, crossing over at the poles more. So, but the beauty of GPM and this international constellation that we have is that it will actually provide a near global coverage of rainfall every 3 hours. And so in places where we have no rain gauges, like over the oceans or even developing countries, this data is crucial to understanding these extreme events that we're talking about.
Absolutely. Thank you for those wonderful questions. We are coming to the end of our program. I have certainly learned a lot of information about severe weather and seen it from different perspectives. Do you have any final thoughts for our students today?
You know, we just had recently a storm at the end of October, beginning of November, called Typhoon Nuri, which was it developed in the tropical Pacific, and it made its way, this is it forming from a Sumi NPP image, and it made its way poleward to affect the North Pacific. Now, up in that area, there were tremendous waves, and the waves were really, really high and really intense winds that actually caused some extreme temperatures in a polar vortex in the center of the United States.
Oh my gosh.
And that triggered snowfall, for example, in Minnesota, all the way through for these frigid temperatures at the beginning of November.
Unbelievable.
And so that's just an example of some extreme weather where you really have to see the global consequences of a storm that developed thousands and thousands of miles away, all the way through to the east coast of the United States, for example.
Excellent. Thank you very much. And we, of course, cannot forget about our guest, Kenji.
Yes.
Kenji, do you have any final thoughts for us?
I think it's just an amazing opportunity to bring art together with science, to perform music and perhaps allow people to feel the earth as well as understand all the information and the data. So it's very special for me to be able to work with science, work with scientists, and bring this sort of a new perspective and way of feeling the earth.
Thank you very much, Kenji. This is actually the final Beautiful Earth program. So we have truly enjoyed having Kenji's amazing talents combined with our NASA scientist perspective. So thank you to Kenji, thank you to Dahlia for joining us today. I hope you all enjoyed learning about severe weather and seeing it in a whole new perspective. If you want more information on how NASA studies weather, you can visit our website, www.nasa.gov. You can also visit the Global Precipitation Measurement Mission education site at gpm.nasa.gov/education. For all of us here at NASA Goddard Space Flight Center, thank you once again for joining us. Until next time, everyone, goodbye from NASA. Take care.